Okay, I don't I don't actually profess to be an aerodynamicist, but I'm being asked by a few people about rocket gliders, okay? And everything you see here, anybody as old as I am would recognize most of what you're seeing here and the kits they represent. Everything here is a glider, and some of this stuff is either handmade or changed from other kits. You can tell that what you're seeing in the back there, that's all handmade. The SR-71 is the Estes SR-71 kit, and this one glides. Okay, this is a knockoff that I made of the Century space shuttle, a handmade X-15, and here's another old Century SST shuttle, and then some Estes kits. So we'll go over why these things apply, or at least my treatment on it. Again, I'm not an aerodynamicist, okay? So I'm not going to go into a whole lot of flight theory. I'm just going to explain in the simplest terms I can why these things fly, okay? Okay, let's start here. This is stick and tissue, and anyone who knows this is the Supermarine Spitfire. Now, the reason I'm showing you this is because center of balance is everything in flight. CG, center of gravity, as it's normally called, is the place that gravity is going to pull down on the vehicle. Now, what I want to show you here is that where this thing balances is incredibly forward of center. Okay? And in order to balance this model, there are approximately 10 pennies in the nose. I had to put 10 pennies forward of the wing, so they're really far up here, almost touching the rubber band. But that was what it took to get this model to balance for flight. And it flies incredibly well, as heavy as it is. And that's part of what I think confuses people when they think about weight in flight. This airplane was actually all motor. That was why it was such a badass plane, because it's motor. It's almost all motor right here. They eventually used the same rig, I believe, in the P-51 and supercharged it, which is why the P-51 has almost the same displacement if you look at it in its shape. At any rate, so you want the plane to have that balance, and that balance, as I said, is incredibly forward. See, it's even forward of the center of the wing. That's the part I want to get to. It's not just important that the balance point of the entire plane is forward, but you have to look at the center line of lift going all the way down here. If your balance is behind that center line, whatever it is for that wing, not necessarily down the center line of the wing, but if your balance point isn't behind the balance point of the center of the wing, your plane is going to throw that weight forward. And that's why your vehicle starts rolling instead of doing what you want. You need that weight forward of whatever the center of gravity is on that wing, or your plane isn't going to work. It needs to have some pull, natural pull down. So that's where we're going to start right there, okay? And if you have that general idea when you make an airplane, even a paper airplane, you'll notice whatever the total surface area of the wing is, the mass, the heavy mass, is forward of that. So in a way, it's that simple. And now we're going to go into it. There are things to consider. When this kind of a vehicle is used, you have to have a dihedral to the wings. That way the mass settles down in that saddle. See, it's pulling down in a V shape into that saddle. Okay? And it'll give you more lift. Okay, let's go into the rockets. Okay, once again, I am no aerodynamicist, okay? So these are the explanations on the simplest that you can get. So here's your basic hand launch glider, okay? The design of it, the swept nature of the wings and everything, that's just design. That's not really an attempt to prove anything. However, you'll see here this model is 11 inches long, and the leading edge of the wing starts at almost 5 inches. I put the balancing point of this wing as close to the center of the vehicle as I could get it, okay? Mind you, I built the vehicle first, and then I decided to balance it, instead of designing the vehicle around a center of balance. And the point is, that I'm trying to make is, you have to balance the plane accordingly. And this is what I mean. It's hard to tell here, so I'll try to put the wing on the back of these bottles so I can show you. Where it balances is on the leading edge of that wing. You see? The balance is closer to the front of that wing. That's important when flying, not necessarily the whole vehicle, the wing. So at the point of gliding, when this thing is on its own flying, you need the balance point right there. When it launches, it's a different story, and we'll get to that in a second. So now we're going to talk about wingless or lifting body type flight. And this is not wingless. This actually has wings. And all that this really is, when you think about it, is a badminton cone. It's a badminton birdie, all right? This one isn't finished, so the balance point is incorrect. Now, see where the wings are. Remember what I told you about flight and where that balance has to be. Well, to balance this ugly thing, it would be very difficult to rig it for balancing. I'd have to put some holes in it, but it should balance right about there. It doesn't right now because it's too nose heavy, see? So when you build something like this, believe it or not, you're going to be applying weight to the back of it in here, because you need to now force the nose up, because this doesn't fly as much as it falls through the air. And so you don't want it to be nose down. If you give it nose down, you're going to get a lawn dart. So you want this thing to settle. And that's basically what you're doing. You're forcing the back down. Now, in flight, you've got the engine stuffed all the way up here, which means the force taking it into the air is all nose. All that force is coming from there, and everything else trails. Once the engine ejects, now the center of gravity, which was way forward with the engine in it, instantly rolls to the back. That's important to know when it comes to making rockets fly. So, this is a real lifting body, and as you can see, there's no actual wings sticking out of it. It is a wing. This is a cross-section of a wing. There's just no wings coming off of either side. So the body is going to have lift, like the airplane I showed you earlier. What you need to consider yourself with is the weight. This is a piece of foam, and it has, I think, 3 BBs in the front, if I remember correctly. So it balances way up front. This would be the HL10. What's in the background is the M2 F3. Now, it's hard to see, but there are coins glued in the inside of this. This is a 3D printed version of this. And again, the balance point is way forward. It's way forward of this. Because now this thing, as it falls out of the air, the way the cone I showed you is not going to work. That's not going to happen. You need to get the nose down because now you've got a wing. And you need that wing to have lift. So just like the airplane, that's got to be over 50% of that wing, which it is. Then the wing will have a power source, which is the gravity of that thing, pulling it down, all the while putting it in the correct attitude to have lift over the wing. So that's a falling vehicle. That's a free falling vehicle now. Its power source is that weight, and it's got to have that wing shape. And by now, everybody's familiar with what Virgin Galactic is doing. Now, their design is pretty radical. I made this as a demonstrator to see if I could actually make something like their spaceship to fly. So I gave it dihedral. I gave the wing dihedral. This is 2 pieces of balsa wood, one curved over the top, one flat. I put the wing more than 50% higher, not a center line. This is like the dihedral on the propeller plane I showed you, where the weight is underneath it, pulling it, kind of like in a saddle. Okay? Now, this is a dicey proposition, because if you put the engine in here, and you put the engine in the back so the nozzle is exposed, and you try to push this through the air, because all of the weight and all of the center of gravity and the mass and the force are right here, you're going to push this thing over end on end, is what you're going to do. So, in order to get this to work, you have to allow the engine to go all the way to the nose, so that the force is up around 50 or more % of the vehicle in the front. Now you have the same effect as an arrow, which is very nose heavy, and that's what makes an arrow fly forward. Once the engine, and while it's in flight now, the center of gravity is way forward. It's way forward. Wherever the center of the mass of the engine and the rest of the vehicle added forward, is where it's going to be. So this thing will probably balance right about there with the engine in it. Once the engine ejects, pop, all of that changes. Now the center of gravity moves more towards the forward edge of this wing, and this thing actually glides like a bird. After I made that work, then I was able to make a model closer to the actual envelope of the vehicle. Now, again, remember, the whole mass during flight has to go forward. So this has a loaded engine. It's got an engine that would actually fly, actually launch, in its configuration. Now, what you're going to notice is, if I try to balance that where it should fly, it's not going to work. Oops, these are flat. Let me try it without something flat. If I try to balance that thing, it's not going to stay. See, it'll flip off my hands every time. Now, once the engines eject, so here goes the engines, they're ejecting. See how far forward they were? So that engine, being more than 50% through this, and especially with the drag here, it has no choice but to go nose forward into the air. That's going to take it into the air. I have this on there because I don't want to destroy the inside of this body tube. Okay, so now the engine is ejected, and now it's time to fly. And we should be able to balance right about here. Oops, if I can get it on my fingers, right? Get the other finger in the right place. There we go. So now it'll glide. So that, and that's what happens with that weight. You put that weight in there, and it's going to topple over. See, it's not going to like it. You take the weight out, and it's back. Put the weight on. No. Take the weight out, balance. So there it is in its simplest form. Okay, now this guy is familiar to all of us. This is the Skydart. Okay, these are great flying vehicles. So why does this thing fly so well? Well, to start with, the launch configuration is very much as I spoke of before. With the engine in here, the weight has to be forward. So since the engine isn't going to be all the way up there and we still need the weight up there, what we did is we made this pod. And in the end of the pod, there's weight. That's a stack of washers. So this is very nose heavy. This pod is very nose heavy, and it goes that far into the vehicle, which throws the weight much farther forward. So to get this to fly, you build this with the appropriate weight so that it's incredibly nose heavy. So at 50%, this thing will definitely, fall over. It's nose heavy. So all you got to do is balance the plane for flight. You balance the plane for flight, and you got it dialed. So where is the plane balance for flight? See? Everybody remember what I said about balancing the plane for flight? This thing is going to be over 50% of the way forward of the wing. Here, let me show it to you with these kind of bottles so you can see the balancing. So the balance is really way forward to the center line of that wing, you see? And that's the configuration for this thing to fly. So I think a lot of people try to balance the center of the plane, but the center of gravity is where? Look where it's at. It's way back there. So as you try to figure out the center of gravity, you have to really pay attention to that wing. That's giving it the lift. And if you look at the amount of balsa on there, all the weight is there. So before you go adding any ballast to this thing after you build it and before you paint it, you want to check that balance. Don't glue the nose cone on until after you've put those first coats of paint on it. Balance it again. The flap on the back, that gives minimal amount of lift. And I'm finding out that this gives it overlift on this particular vehicle. That's why the screw is in there to force it down a little. Because if you give it as much lift as that wedge will give it, this thing will just flip through the air. And now that you're armed with that information, the rest of this should kind of make sense. So here we got two different kinds of rocket with glider recoveries. This one's obviously going to have a parachute assigned to it. So it's a rocket with two gliders, is what it is. So this is pretty obvious. Once there's a separation and the gliders detach, it's a whole different vehicle. So you're going to build this like a rocket, just exactly as the instructions say, and then you're going to balance these as was mentioned before. So where are these wings going to balance, right? Or where will this balance? Well, if I'm right, then it should be over 50% of that wing. At over 50% of that wing, is where these gliders should balance. So if your balance is over 50% forward of the wing, so it's not really important where on the glider the wing is. It is, but in these simplified versions, not so much. As long as your balance point is 50% forward of that wing, okay? It's all the same on every one of these vehicles. They're built the way that they're built so that the drag on launch is really in the back. You got drag, and the drag can be the equivalent of having that nose weight. Because if you have the drag, just like on an arrow, when you shoot it, it's going to right itself in the direction of flight. So once the model is built, and you just need to consider yourself with the gliders, if you have the whole forward center of gravity forward of the center line of the wing figured out, you're going to achieve glide. You're going to get it. Try to get some better shots here. So, and that's how you get glide out of all of your vehicles. You just have to remember the center line of the wing issue. So here's the center line of the wing. Look where those bottles are, really far forward. Now how do you deduce that? Okay, you built it, man, but how do I know where far forward of that wing it is? Well, start by finding the center of the wing. That's where you're going to start. And I don't mean take a ruler to it, although you can. You can take a ruler, but this wing is 3.5 inches long. So from 1 3/4 inches forward is where you're going to start. So that's where you're going to start to try to balance your plane. Your glider is by, saying it's got to go forward. Then you're going to start test launching it until the thing glides the way that you want it. So, now that you get it, the engine and the force during launch is farther forward of the center balance of the wing on this model, because both of these glide. So this is scratch built, so it doesn't have exactly the same dimensions as the other, but that's only where I decided to mount the wings on the gliders. So again, the force of launch is forward of the center line of the vehicle. Once the engine has ejected, once the pod has ejected and the two vehicles are separated, now you've got two vehicles that are going to change center of gravity simultaneously. Now that they're disassembled and the pod is gone, their entire mass shifts. The whole centers of gravity change. So when you build this model, one of the things you're going to be concerned with is where that center line is. Where in the world is that center line? Well, on this model, this wing, it's an 8-inch long model, and at 4 inches, we're just behind the center line of that front wing. And we should balance up close to the leading edge of the wing. See? Farther forward, farther forward. See that? So where did the center line of that one go? It's radically forward. So to counter it, we give it a little bit of down force in the back, which is almost negligible during the launch. But during the flight, between all of those parameters, the fact that I have some short, fat wings on this puppy gives this thing enough lift that you really don't want to try to chase this thing down. It goes a long frickin' way, okay? Well, what about the carrier? So, if he's right, then the balance point is forward of the center of the wing. Holy Toledo. Just how far forward? Oops, am I on the other side? Try to balance that out. Of course, I'm trying to do this looking through the camera. There's a real engineer for you, huh? So, as you can see, again, the balance point is really, it's almost the leading edge of that wing, because this is all of the lift. This is cantilevered off the front, okay? The two forward wings, they're not really giving lift as much as being, control surfaces. And again, you'll notice the flaps. They're permanently there, but they're negligible during flight, okay? One of the reasons is they're on a kind of a softer hinge. So they slightly lay flat, not flat, but down as it goes into flight. Now, mine, I've given mine a slight, super slight difference in the angle on both of those flaps. Very slight. So that I didn't chase this mother across the county. That's why these things don't launch with anything more than a B engine. So there's pretty much the crux of how these things fly. You have to have the force, which will change the center of gravity forward of this puppy while it's flying. After it comes off of there, that whole center of balance now moves backwards. It's instantaneous. This thing does a massive loop. It does a huge loop. I couldn't even tell you how big the loop is. And then it lands after one loop. This thing, well, you're going to be running after it for a while. And so now you have something scratch built, like the X-15. You want to try to make it as scale as you can, but you do have to be forgiving of it, because you just may not get what you wish for. So I've scratch built this and designed it exactly the way the others are. Heavy weight. This is screws, literally taped down for the test flights. And then the glider. I wonder where the X-15 balance is at. Uh-oh. We are really far forward of that center line. So, scratch built, with the experience that I have, I know that this glider glides as long as we are at that 50%. This glides very well also. This has been repainted and rebuilt, I don't know, 50 times? No, that's too much. 10 times, right? Okay, and last but not least, one of the other model builders gave me this for completing a model for him. And anyone will recognize this. This is the Estes SR-71. And most of us put it together with the parachute. You don't have to. As long as you build yourself a pod, which has the weight in the front, you can launch it. You'll have to recover the pod, but as long as it balances, why it's tough to arrange it on this. Let me put it there. As long as it balances, forward of that wing, and yes, this thing glides like a mother, you're going to achieve flight. Where is it? Well, a lot like the Spitfire. It's so far forward on the wing, it's almost absolutely at the leading edge. Why this thing flies, by the way, is because all of the lift that you're getting off of that body, that's all wing. It's all wing, the whole body, everything. So you can put it together with the parachute because it flies really nice. But if you want that level of scale to get this thing to fly, just don't put the engine pod in there. This was not balanced with anything. This is the kit just assembled. And again, it flies like you wouldn't believe. Now, should I be able to get some video of all these things flying, flying, I will post those too.